Again, my name is James Kubli. I'm an applications engineer here at Saratech, specializing in Femap support. Today we're covering gap elements. We've got a few subjects here. We're going to cover first exactly what are gap elements, how we go about defining them, and I've got a few different demonstrations to show. And then at the end, kind of some key takeaways to remember when dealing with gap elements, followed by the Q&A. So gap elements, the most simplest way to think about them are just single directionally dependent spring elements. They can provide stiffness in either compression or tension. We can even apply a preload for this. But keep in mind, there are some limitations to the use of it, like linear only supports compression, but nonlinear supports both tension and compression. So the way this occurs within Nastran is we've got two nodes here, GA, GB, over on the right-hand side. A stiffness is applied between them. This KA here represents compression stiffness. There is a KB for tension stiffness. GB or GA, in this particular case, can move either towards each other or away from each other. And depending on what sort of initial gap we might have defined, once that initial gap is closed, and in this case, the initial gap is the distance between GA and GB, we'll see that the stiffness is then applied between these two nodes in this particular case, compressive direction, KA. So, as I mentioned before, GA, we're going to stick with the terminology of GA, GB, and the KA, KB, simply to match the way Nastran is referencing them. So GA is generally the from node, and GB is the to node. This is important because the vector of GA to GB creates the element positive x-axis. And so this is going to be the compression tension line of action is going to be along this vector. But like other line elements, orientation need to be defined. Even though we may only be dealing with compression or tension, we still need to orientate Y and Z. So that can be done in a few different ways: a vector, or referencing an existing node, or even a local coordinate system, which is going to be pretty mandatory when it comes to coincident GA, GB. So you don't necessarily have to have a physical length to it. They do work with coincident nodes, but we talked more about that in a previous video I did on using gap elements for contact in nonlinear. So we're not going to be trying not to overlap or duplicate some of that in that video, so I highly recommend watching that if you want to learn more about that. So then we get to when you define the gap property. This is the window you should see within Femap, the property card here. We're going to be covering mostly the left-hand side. We're going to actually be only covering the left-hand side of this property card. This was related to the nonlinear and contact for the most part. It does have effects on friction, and of course that bottom right-hand corner is not related. So initial gap is important. This is the amount of motion before stiffness is applied. So GB or GA relative to GB needs to move this initial distance before stiffness is applied, such as compression or tension. As you can see here, we've got compression stiffness, that's KA on the property card. This only affects when the two nodes move to get towards each other. We've got KB, which is the tension stiffness. This is, of course, when they want to move away. And then there's transverse stiffness. This is KT, a lateral stiffness. This is only effective when the gap is closed. In Femap or Nastran, we'll either use the transverse stiffness or a friction. So with that, let's talk about the friction here. There, you'll notice that we've got Y friction coefficient and Z friction coefficient of friction. Now, it kind of depends on what type of analysis you're running. Again, like the transverse stiffness, it's only effective when the gap is closed. If you are running a solution 106, that is the only time Z friction is available for you. And if you are running a solution 106, Z friction can behave in two different ways. If you have adaptive turn on there, and that means you have like max penetration, some additional values in there, just having this box checked here does not really enable the adaptive stiffness. You need like a max penetration for that to function properly. So with adaptive turn on, the Y friction coefficient is your static, and the Z friction is your kinetic friction. If adaptive is not enabled, then basically you get two different direction frictions. You get your Y friction coefficient in the Y direction. That might be more important to make sure that you define your Y direction appropriately. And then of course Z is automatically calculated from there. And then lastly, we have a preload force, which is just the initial force that NASTRN will apply on the gap element. I got a little asterisk there. We will talk about that asterisk in the demonstration. So let's jump into demonstrations here. Oops. I hit tab one too many times. There we go. So I've got a very simple model here, simply because it runs quicker. For presentation purposes, it is a 1/2 inch by 1/2 inch steel bar, and it is 10 inches long. We're using steel, of course, and so right now I've got this end here. It is free to pivot about the Z-axis here, so we're going to be relying on a gap element right here to prevent our motion. So we're going to cover just real briefly a bit about defining the gap elements for the beginning. So let's go with our property here. Let's start off with just compression, since that is the one that's most often used or people are most familiar with. We'll put in a stiffness of like 1,000 pound-force per inch and click OK here, because we're just going to first demonstrate some compression. Model element to create our gap element here. Change our property to gap. Now we just need to define our nodes. So it doesn't, unless you have multiple elements, multiple gap elements functioning for like contact, which again I talk about in the previous video we've done, it's not going to be super important which one is GA, GB. Whether these two nodes move together or away is going to have the same effect. But for the purpose of this demonstration, I'm going to try to stay consistent with GA being the constrained node and GB being the node on the element here. Now, right now, orientation is just asking for a node. I can click on vector here if we wanted to, but I'm just going to click any node on our beam element. This is going to make X direction here and our Y direction that way, and Z is going to be off another. We won't be looking at any results that are dependent on those directions, so not super important. For the most part, when you're setting these up, they aren't really important, but unless you're including friction. So there we go. We've got ourselves a gap element that's set in compression. Let's go ahead and apply a load. I've got this already defined, so let's go positive Y here. So now you can see I've got a load here of 100 pound-force in the positive direction. Again, the Z rotation is free on this end, so we should be able to move up, and all we're going to see is our gap element there resisting that. Let's go ahead and set up our analysis. We'll set this up as a nonlinear static. I'm just going to click OK. Most of the default options in there are fine. There's only a couple things we need to modify. That's going to be our nonlinear options. It's going to default to 0. Because this model is so simple, I'm only going to tell it to do 5 increments. But unfortunately, because there's only 5 iterations before a stiffness update, NASTRN won't necessarily function right all the time with such few increments when it's dealing with gap elements. So in this, because of the simplicity in the few increments, I'm changing the number of iterations before update to 1 to get it to function right. So usually with a nonlinear analysis like that, you'll need more iterations, and that won't be a problem here. Now our boundary conditions, just to make things simple, I'm just going to change this to use active set. So all I have to do is change the active load and constraint and then rerun the same analysis. All right, with that, we've got a very basic, simple compressive gap element here functioning. Give it a run, should be done here. We can take a quick look at those results, just verify that it did what we expected it to do. And there we go. We are seeing a T2 displacement, or our Y displacement, upwards in the direction of our force, and we are getting a 0.1 displacement, which should be appropriate. Remember, we've got a force of 100, and if we take a quick look at our gap properties down here into the editor, you see we've got a stiffness of 1,000 pound force per inch, so 100 with that should give us a 0.1 inch displacement. Wonderful, except for that sticking yellow dot. All right, so now let's go ahead and demonstrate tension here. And with that, we're just going to cut this over, paste that right over there. Let's reverse our load, and we should be able to run this analysis without an issue. Or, as you're going to find out here in just a second, we would think it'd be without an issue. Let's take a quick look at what happened here. Looks like we failed to converge. That is not very expected. Now, it is very odd, and I would call this kind of a quirk with Nash trend here. It doesn't seem to be too happy with dealing with tension here like it can in compression if all it is the gap element that's resisting rigid body motion here. I haven't been able to figure out why. I test this back to version like 2022. 2022 ran, gave me appropriate T2 deflections, but it also gave me some bad additional deflection results. So there's something very weird about a model that relies purely on tension to run. There is kind of a cheat to this. If I put a small compression stiffness in here, the analysis will run. Now, what I found through testing is this compression stiffness is kind of relative to this tension stiffness. If this value was larger, I would need to use a slightly larger one here. So if I went with like my stiffness happened to be 100,000, I'd have to up this up to 0.1. Now the ratio of these two don't seem to be very fixed. If I was running this at like 10, you would think if I set this to this value here, it would function, but it does not. So, but a small value here seems to be what you need to get this to run in this particular use case. That seems to be, I have not encountered this particular use case where you're relying purely on tension only. Usually I have a preload applied to the model, and that doesn't seem to cause a problem. So here, with that small stiffness and compression added, though technically a larger value should have not had any effect because we weren't going in compression. But just in case you had a model where you had multiples of these where some might go into compression and you want that in slack, you're going to have to use some sort of stiffness there. But we can see here our displacements are appropriate. We've got that 100 pound force downward, and we are getting a displacement of negative 0.1. So yeah, it seems to be only in this particular load case here where you're only relying on that situation here. So let's go ahead and let's take a look at applying a preload to the model. So let's go back to compression here, change that, and we're going to add a preload of 100 to the model. And right now we're going to take we're not going to use a load. We're going to rely purely on the preload to create our load, and we're just going to make this, we're going to switch it over to fixed. So this end here is now fixed, completely fixed, and that end over there is completely fixed. That way, just in case we don't run into that issue again. And let's give this an analysis, a run here. It takes a moment. All right, so now we've got some of our beam deflection applied. We can see that our preload, even though we're in compression here, pushed the model down. We got a small amount of deflection of 0.2249. We do not end up with the full 100, well, sorry, I apologize. It's going off on a different subject there. Got ahead of myself. So we are seeing a bit of deflection on this model from the force preload in the compressive. It is pushing it down, kind of what you would expect with a preload. Now let's give this thing a try with tension here. Give that a run. Again, still, we only got that preload. Let's see what happens. All right, looks like our analysis finished. Oddly, even though we are in tension here, we are getting the same load. So this is to show that, unfortunately, that preload force only seems, or that preload force is working in the positive X direction of our element axis. So you may think like, oh, okay, so that works in the positive X direction of our element. What if we change this to negative preload force? Is that how we're going to get our tension in our model? Let's give that a quick run and show. We ended up with a fatal error. And if we take a quick look at our fatal error, it gives us legal data on bulk data entry. Basically, if you take a look at the quick reference guide, you'll find out that the preload does not support negative values. It needs to be 0 or higher. So that leaves us with a problem here. How do we get preload for a tension only gap element? So there is a way around that. Let's go back over here. Let's edit our gap property. So instead of a preload force, what we can do is we can set an initial gap. Now, if you remember, if you saw the gap for contact or in nonlinear, how to use gaps for contact, the initial gap here is basically a distance the element can move, or GB can move towards GA before stiffness is applied. But thankfully, initial gap can actually support negative numbers here. So if we set this to negative 0.1 here, that should give us our 100-pound force. Now it's going to be negative because the initial gap, oddly, works in the negative x-axis. So our preload force here only applies in the positive x direction of the element, and our gap here works in the negative x direction of our element. So we've always got to remember that and keep in mind whether we want positive or negative here. So if we put a negative value here of 0.1, do that, run our analysis. Should just take a moment here. There we go, converged. Did we not? 100, okay. I apologize here, I must have made a mistake. We are fixed. Negative 100 tension stiffness. Push. Did I get that backwards? I always do that. I always get these backwards whenever I'm doing this. Now, I get it. Negative X, tension. It's always that equal opposite force thing that gets me confused. I always have to sit there and think about it at times. So I apologize here. Let me try this again. See if I was thinking about that wrong. There we go. Yes, I did. I was thinking about it wrong. I apologize. Got my head wrapped around it backwards again. It's always that equal and opposite force thing, depending on what you're looking at and where you'll see it. Okay, so now that we applied that to our model, We're not going to see that 0.1 because we are still fixed over here. So we should see the same thing as if we had no gap element and 100 force, well, almost 100 pound force being applied here. Now remember, as the gap element gives, or as our model gives, because that is a spring force, as our spring relaxes a little bit or doesn't fully contract or expand, it will actually reduce the final force applied to our model. But I believe in this case here, because my beam is so thin, it's only a 1/2 inch bar and it's 10 inches long, it is pretty close to giving us that value there. So yeah, we're getting 30.72 is our final preload, and we're getting -30 over here. So you can see we're not getting that full value. That's because the model is giving. We're getting some deflection here. And if we looked at this deflection, we would see a reduction in our full applied force. So you can always fix that by doing a little bit of math, calculating what additional, if you just do a linear assumption, so like if no spring force versus the deflection here, find the deflection, and then find out what your actual final force was. You can always work backwards there to find out what kind of initial gap you'll need to create that positive, to get that final preload force that you're actually looking for. Okay, so we've covered issues with preload, how it only works in one direction. Our initial gap here can work in multiple directions. We can actually still even if you want to see what happens with in compression here. If we had this negative value, we can do that. But based off of time here, we're running out of time. But yeah, negative values can be supported with the gap. So if we had this in compression and we put a negative value in there, we should see this thing. It should behave like an interference fit and be pushing our model outward. You know what? We got enough time here. I think we get to squeeze this in. Let's change this to a negative here. Let's put our value over here and there. So that should behave exactly like putting a 100 pound force preload there. Yeah, let's go ahead and analyze that. We should basically see the same deflection, just in reverse. And we can see the reversal of the forces, 30, -30 here. We can go back here, look at our T2 translation here, and see, yep. So basically compressive, it just pushed it away as if it had that preload force. So with solution 106, you can use either or. With the preload force and limitation, it only really works in one direction, but with the initial gap, negative values work. So you can have both a pushing force or a pulling force, depending on whether you're using compression or tension. And it could also work as slack, so to speak. So, but let's take a look at linear here. Linear is a bit different in the way it behaves. Linear does not support tension, but you still may want to run your model in linear because you don't want to deal with gap elements for contact, and you've got contact in your model, but you still want to be able to model tension elements, such as like strapping, for example. So there is a cheat to do that. And what you see here is I've got a couple extra nodes. And the way to do this is we're going to overlap two elements. We're going to go from this node to this node, from this node to that node to create two elements that overlap. And between it, we'll have our gap element. So what will happen then is as this tries to pull away, it'll pull these two nodes together, and this will actually behave in compression. So that's how we can trick or use a compression-only element to behave in tension. Now, there are some weird limitations that I've run into with the different types of elements we can use here. So let's go with one of them, and let me show. So most likely you probably want to use like a rigid element here to define this. But there is a particular problem with this. Now, hopefully I won't mix it up in my head here for the practice here, but you've got your independent and your dependent degree of freedom here. If I get this wrong, it's just a reversal. But if I remember correctly, independent here is going to be here, and our dependent is going to be there. Degrees of freedom don't really matter here. You can limit it to only the degrees of freedom or use them all in this particular case. But we'll go independent and dependent. Now, if you reverse this, you get this funny fatal error that I've not seen before. And we'll see if I end up accidentally creating that myself, because I accidentally got that wrong. So let's go ahead and define our gap element here. Nodes, GA to GB. Orientation still remembers what I last picked, but we'll just go over here, just some random node, and click OK. So now we've got our gap element here in compression. And let's take a look at our setup here. Okay, so I have 1,000 compression stiffness here and a 0.01 initial gap here. So negative, so that should be creating an interference force here if I've got my head wrapped around this the right way. We got no other load here, so that should kind of create it should pull these two together. So let's move this to a static analysis. Okay, it should automatically, boundary conditions, yeah, we've got no load. We're relying purely on that tension there, or that pre-tension on it. Let's give this analysis a run. Bravo, I did not accidentally reverse my rigid elements. But I did get my stiff or my gap sign backwards. So I like using these initial gaps, but it always takes me a moment to remember which direction I want this to be in. Let's give that a run. Or if I'm remembering this incorrectly, I am remembering something incorrectly. I apologize here. Let's go with, let's take that out and let's just go with initial preload, 100. That should give us our preload down. Okay, I apologize. I'm not sure what I'm doing wrong here. Did I get compression tension? Yes, preload. That should have worked. Gap element in the right direction. Challenge of doing demonstration live. I must have misclicked something somewhere and did not get this model defined properly. I promise you, it did work this morning when I was practicing. So again, sorry about that. That should have worked. Give me a moment. I'm trying to think of what I might have made a mistake with. Very frustrating indeed. Well, if you saw my mistake, let me know. Because off the top of my head, in the heat of the moment here, I don't recall what I did wrong. Well, that concludes our demonstrations there. Sorry for that last one there. I know it works. Anyways, to the nonlinear. So preload force in the property card, keep in mind that works only in the positive X element direction. So a negative and if you try to use a negative preload force, it'll give you a fatal error. So don't recommend that. So a negative value in the initial gap can create that same sort of pushing force that preload creates. or in our case, sorry, that should have been a positive value. Initial gap direction is in the negative X element direction, so compressive. Keep in mind, though, that when you do apply an initial gap like that to force a preload, either a compressive or a tension preload, as that spring element gives, that value will be lost a little bit. You can also still use negative values for slack. Either displacement needs to be closed before compression stiffness applies, like there's a gap there, or there's a slack in your tension from whatever strapping you might be using. Tension, and something I didn't demonstrate in this one, but I did demonstrate, I believe, in the nonlinear or the previous video I did on gap elements as contact, is tension and compression forces from the gap element do not update with displacements, so be careful of large displacements. Now, in linear, gap elements function as either bidirectional springs or as contact. Oh, that's what I forgot to do. That reminded me. There, I had it in my takeaways and I forgot it in my analysis step. The only way to get spring elements to work properly, to get them to work, otherwise they work as bidirectional. Go back into there, edit. You do need to check this box off for gap as contact. That's what I blinked on. We'll click analyze here and hopefully that should work. We've got a preload force. Oh, it finished. I didn't even, it was so fast I didn't even notice. Come on, right? No. Okay, apparently I'm still mistaken here. But yeah. Apologize. So yeah, gap as contact must be enabled in order to get the compression only to work. Oh yeah, preload force is ignored. That's another problem. That's why I started creating multiple mistakes. Once I made that one mistake here, preload force 0 or 0.1. That's the amount it needs to go. So we go with negative, if I remember correctly here. Analyze, solve. And we're over time here. My apologies. There we go. Now we get it. Now we've got our tension preload applied. Sorry, live presentation, I blinked on that step there. So negative value initial gap can create the same pushing force. Also keep in mind, tension KB is ignored. That's why we had to use that compression only. We can't use tension stiffness. And we also still want to remember that initial gap direction is that negative X element direction for that compressive direction. Friction also has limitations. We talked about that before, about that setup. So if you want to use friction, you're probably better off just using contact when it comes to linear. So for gap elements in linear analysis, I think their best use is simply to replicate a tension-only load in that particular case when you're trying to model strapping or rope, that sort of thing. So again, so that brings us to our questions. Again, sorry for fudging the linear there and blanking on the limitations of it.
It's all good. That's why your key takeaways came in handy. So we had one question come in during your demonstration, which I apologize if you already answered it during it, but it was, is the constraint pinned for this example?
Which was that the linear or the nonlinear? I believe for the linear one here, it is they're all fixed. And after that initial one where I was showing how the tension only with the load, that one was the pinned here with the fixed, and then this one was, and then I switched over to fix to rely purely on just the preload force pushing against our beam element.
Okay, thank you. And then next question is, How do gap elements function in the multi-step nonlinear solvers?
The multi-step, the nonlinear, is similar to the limitations that similar-ish to linear static. Basically, what you get, all you get is Ka and Kb. That's your compression and tension and the initial gap. Preload is ignored, so that, and friction is not used. So no mu or Y friction or Z friction, and also adaptive. None of the adaptive settings work. So as best as I can tell, adaptive stiffness isn't available in the multi-step solver, because in order for adaptive to function, you've got to define like a max penetration or something like that. And those values in the property card are ignored. So therefore, my assumption is that adaptive doesn't work in the 401. But you can still use them as like a tension only element or a compression only element if that's what you're interested in.
Okay, thank you. That is it for questions.